So this is the H axis, which is equal to Ni by L of the magnetic material, and B is in Weber per meter square. Weber per meter square. Now, if such a material is excited by alternating current, so initially if the magnetic material is not magnetized, this curve will start from 0, this way it will go, then it will come here, and after that it will be within this loop. The V value will change according to this current I. Now, hysteresis loss can be shown to be equal to the area represented by this curve. That I am just going to tell you how it is like that. Let us suppose that the coil, and it is wound on a magnetic material, and I am passing through the coil a time varying current, in fact sinusoidally varying current I, and I want to find out, estimate the value of the hysteresis loss. And let us, for the first time, let us assume the thing starts from this 0 current, and there is no residual field in the magnetic material. Where is the magnetic material? Magnetic material is here, on which this coil is wound. This is the magnetic material, that we know. Now, as you are increasing current, that is H, applied in the magnetic circuit, the value of B will go like this. Suppose at any time the value of the current is I here. I want to find out how much energy is being inputted into this coil. So to find out that, what I will do, this coil, since current is changing with time, will have some induced voltage induced across this coil. Suppose at any time current magnitude is this much, which will decide what is the value of H, which is Ni by L, and the corresponding B is this much. Now suppose, so at time t, the current is I, which will give you a particular value of H, and the corresponding value of B is B. That is, this is B, this is H or I, like that. Now suppose a small time goes, t plus dt, current becomes I plus di, and H becomes H plus dh, and there will be an increment in B to B plus dB. Now, if this time dt is very small, the voltage induced in the coil, E, is given by the number of turns of the coil, N, into d phi dt, that is d dt of B into A, where B is the flux density in the core of the material. That is known. Now this A can be taken out, An into dB dt is the induced voltage. Now, whether a particular element absorbs or delivers energy depends upon the polarity of the voltage and the direction of the current. For example, in a circuit, if you have a battery with this side plus, this side minus, if current really flows in this direction at any point of time, then we say the battery is giving out power to the external circuitry. It is delivering power. On the other hand, if in the battery the voltage polarity is like this, and current enters through the positive terminal and comes out from the negative terminal, then we tell that this battery is now absorbing energy or being charged. It is true for any element. Okay. For example, in a resistive circuit, if this is plus, this is minus, current flows like this, the power will be lost here in the resistance. Power is absorbed. So similar thing I will do here. Now actual direction of the current, if it flows from this to this, is suppose the positive current, and the polarity of the voltage induced is this side plus, this side minus. Obviously the power at time t is E into I, and let us consider the variation from 0 to the point A via this path 0 A B. So during the journey of B from 0 to B via point A, the polarity of the induced voltage will be positive. Really this is plus, this is minus, because the slope of dV dt is positive. Okay, B is increasing in nature. Therefore from 0 to B, the power delivered to the circuit is EI, and in time dt how much energy has been given to the coil? This into dt. Energy supplied to the coil over time dt is voltage at that time, current at that time into the time. So this is the amount of energy supplied to the coil. Now you substitute the value of this one, the value of E, which is AN dB dt, into this I is there, into dt, which can be written as A into L into Ni by L into dV. So we write elemental energy supplied to the coil in time dt, in time dt is suppose some dW I write, and this is equal to nothing but AL into H into dV, because for Ni by L I can write H. For Ni by L I can write H. So during this journey 0 to A to B, what is the total amount of energy supplied to the system, to the coil? Total energy supplied to the coil to reach point B. This is point B from O via A will be the integral H dV with appropriate limit. What will be the limit in this case? I mean 0 to some B max here, whatever is the B value there, it will be this. Now if you look at this diagram, I mean I will draw side by side here. This is the curve, the BH curve of the material. This is H, this is B. To reach from O to the point B, the amount of energy supplied, this H dB integral, is nothing but this area. This point I called A. Okay. To avoid confusion, this B, let us write B dashed. This one B dashed. The point B dashed. And this is nothing but the area 0 A B dashed. Let us call this point M O. This area, amount of energy supplied to the coil. Why I say the energy is supplied? Because current direction is really positive, it is entering through this. And the value of the voltage existing in the coil is this side plus, this side minus. Why? Because dB dt is positive. B is increasing with time. So rate of change of B with respect to time is positive. Now suppose after this current is being decreased, so the point moves here and an amount of energy received is given by this area. Now current decreases because sinusoidal nature of current starts decreasing. The point of operation will now move from, will follow this path, That is, now from B dash it will come to C. So in its journey from B dash to C, now journey from B dash to C, Draw the coil once again. At that time, is the current positive? When it is coming this way, positive, because H is positive. So current really is entering through this terminal. Is dB dt positive? No, B is changing with time. So polarity of the voltage induced across the coil is this one. So far as the coil is concerned, is it absorbing energy or delivering energy? It is delivering energy. Like a battery, through the plus terminal current is coming out. So it is delivering power. Delivering power where? To the source. Pumping back power into the source. Tell me which area will represent this amount of total energy supplied to the source? B dashed, AM, C, B dashed. I mean, if you want to pinpoint it, give some name on the path so that journey from B dash to C via D, the amount of the amount of energy fed back to the supply is given by this area, double-hatched area. Back to the supply is nothing but the area B dashed, M, C, D, B dashed. This area, which is double-hatched. Therefore, we can see the amount of energy returned back to the supply is less than the amount of energy received from the supply only during this journey. Therefore, some amount of energy will remain in the coil. Now suppose so this way it will continue. Now what I am trying to tell, if your circuit has started even from 0 B value, after that it will trace its path through this BH outer loop like this. Are you getting? Once the current is changing with time, no matter from which point it has started, finally the thing will be like this. That is, when current changes, this is H or I, and this is flux density B, it will traverse like this. So in that case, once again following the same rule, you see when it does so, we will break up this journey when the current is positive. That is, let us call this point as, say, P, this point as Q, this point as R. So when current changes from 0 to this maximum value and B value changes from P to R via this path, how much will be the energy now supplied or received by the coil? Energy will be received because I is positive, dBdt is positive. So which area will give you the amount of energy received? When the current changes from 0 to I max, it will be this area, HdB, this area. Okay. Then after it reaches I max or H max, current decreases, and so long current is positive in this zone, current direction in the coil is still positive because H is positive, current is positive, but dBdt has become negative. So this is the situation now in this zone. So the amount energy will be fed back to the supply, and how much will be the energy fed back? That is this area, and this I double H. In the second case, the current is totally negative, that is this zone, from this to this. Current is totally negative, means actually current is entering through this other terminal. And what about dBdt? It is negative, so this side plus, this side minus. So when current once again starts building up from 0 to minus I max, here, what will happen to the energy? Will it be an absorption of energy? Absorption, because through the plus terminal current is pumped into the coil. And what will be the magnitude of that area? This will be HdB, once again this area, this whole area. So it reaches this point now. Then once again when current comes down from I max to 0, H changes from H max to 0, then current direction still remains negative. But what happens is this dBdt becomes positive here, from this to this. So the situation will be like this: coil, this is plus, this is minus, and current is negative. So which area will represent that amount of energy delivered by the coil to the supply? It is this area. And this thing continues. So in each cycle, the some amount of power is absorbed by this one and dissipated as heat inside the material. And what will be that amount of energy per cycle? It is this area. I think this was like this. Huh? So this amount of energy will be the area inside the BH loop. Therefore, we find the area of the BH loop represents hysteresis loss. That is, if you choose a magnetic material, you find out its BH loop, which you have done perhaps in your measurement lab, those who have taken up. This area will give you the amount of power loss. Now remember, in this case, we have taken up this H into dB, and there is AL, an amount of energy actually dissipated. W is what? W is AL into this integral h dv, is not? So after you calculate this area, with what you have to multiply? With the volume of the magnetic material. L is what? Volume of the magnetic material. Volume of the core. So what they say is this area is the amount of power loss per unit volume per cycle. For one cycle, this much of energy will be dissipated. Okay, so you find out the area. If you know the total volume, multiply with that. If you know the frequency of alterations of the current, that is 50 hertz in our case, we will multiply with 50 to get the power loss per unit volume. I mean, total power loss I can calculate as hysteresis loss in a magnetic material. Is that clear? Now, only thing is, you have to know the characteristics of the material before you do that. And your intention will be to make hysteresis loss as small as possible. Therefore, while constructing any electrical machines involving magnetic material, you must see that this area is very small. That is, given two materials with one BH characteristics like this and the other this kind, you will definitely opt for this one, because the area enclosed by the BH loop will be less, your hysteresis loss will be less. Now, apart from this, once again it is Steinmetz who, after doing several experiments, he gave one formula which is not derived mathematically, but after doing several experiments on different kinds of magnetic material, he told that hysteresis loss can be estimated by using this formula, that is Bmax to the power n into F into some constant Kh per Steinmetz formula, which is not derived. What these formulas are called, which are not derived? Some empirical formula, you are right. So it is an empirical formula, he suggested, and he told that this Kh will be a constant of the material, and this n can be between say 1.5 to 2.5 depending upon the types of material, etc. And F is the supply frequency. One can use this also to calculate this hysteresis loss without obtaining the BH loop. And what he is ultimately suggesting is that the difference in this way, if you calculate, the difference will not be much. This was obtained after doing several experiments on different kinds of materials. Therefore, now to summarize the core loss, as we have seen, it will comprise of eddy current loss, eddy loss, which will be proportional to, as we have seen, Bmax square, F square, and thickness square, And this unit also, if you remember, was the amount of power loss per unit volume. If you go through earlier notes, per unit volume. And hysteresis loss is proportional to some, either the area of this coil, area of the BH material, or if you go for this approximate empirical formula, it will be proportional to some Bmax raised to the power something. For ferromagnetic material it is 1.6 something like that into F per unit volume. Now, in a transformer, if the transformer is energized from rated voltage, I will ask you now some few questions, you answer me, so that I understand you can make it, hopefully. Suppose you have applied the primary of a transformer with rated voltage, rated frequency. Secondary is not loaded. Secondary is not loaded. Supply frequency is known, fixed. You have applied rated voltage. So, there will be some Bmax generated inside the core of the transformer. And therefore, there will be some eddy current losses and hysteresis losses together taking place under no load condition. Now, suppose I load the transformer. What is your comment about these losses? Will they change from the amount of core losses which was taking place during no load condition, or will it vary substantially? In a transformer, you should remember, from no load to full load condition, do you think Bmax will change? Bmax will practically remain constant. Supply frequency is constant. Magnetic material volume is constant. So, the core losses remain practically same whether the transformer is operating under no load condition or under loaded condition. So, this we can just conclude from this, because in a transformer, you can write in a transformer, at least in an ideal transformer, so far we have studied in a transformer, phi max or Bmax remains constant from no load to full load condition, from no load to full load condition. Therefore, core loss in a transformer will remain practically constant in transformer, no matter whether it is loaded or not, because it depends upon Bmax and F. Now, in a transformer now, if I want to take the core loss into account, how do I do it?
This one is only for ideal transformer.
Which one?
This point, sir.
Ideal transformer, it is definitely like this, yes.
So for real transformer?
I will come. It will practically remain constant. That's why we say in a real transformer, it will practically remain constant. Why it will be slightly different will become clear after I incorporate the resistance and leakage flux into the transformer. Why it will slightly change, that I will tell. Okay. But in an ideal transformer, it is true from no load, absolutely true what I mean to say. But in a practical transformer, I will show you right now after some time that this core loss may slightly change from no load to full load condition. Okay, that I will show. Now let us come to the how to take this core loss into account with that transformer which was not so ideal, where mu r was finite. Okay. Now in a transformer like this, so now in this transformer I am bringing another realities now. That is mu r finite. Mu r finite is already I have taken care of, finite, and core loss is present. Core loss is present. First thing, what your observation will be. Suppose in a practical transformer like this, having these two things, of course winding resistance, leakage reactance are not present. If you apply an AC voltage here, and if you connect an ammeter, and if you apply this voltage, what will happen? This transformer cannot draw a current which is 90-degree lagging. Because even when the secondary is open, some wattage is to be drawn from the supply, because core is getting heated up, is not some real power. Wattage must be drawn from the supply. Are you getting? Because in eddy current, this way we can think. Suppose this is your applied voltage. This is your applied voltage. This is the flux produced, 90 degree. Some Im is there. But apart from that, because of the core losses, there will be some current, reflected current. Because the eddy current loss, for example, is just like loading the transformer with another coil, which of course we don't want, but it happens inside the core of the transformer. There will be as if some secondary current, and this will dictate the primary to draw some extra current. So that induced voltage in the eddy current could be represented by 90 degree lagging, some eddy voltage, some eddy current in this actual core, and it will have its reflected part like that. So the transformer is as if loaded whether you like it or not. Secondary is open, things like that. And also some wattage should be drawn from the supply. So what will happen is this supply voltage, the no load current will be not really lagging. This I will denote it by I naught, is called the no load current. Will not be lagging exactly by 90 degree, but by some angle, perhaps close to 90 degree. Because when you design a transformer, you take care that these core losses are kept to minimum. Now, this current can be broken up into two components. One is perpendicular to this V1, another is this one, in phase with V1. This current can be broken up into two components. One is Im, another is in phase with V1. It is this current Im which we can attribute will establish the core flux, and this current will be responsible for the core losses in the transformer. Now, how to take this into account? This can be taken into account in this way. This is your applied voltage. First I draw the equivalent circuit. This is your applied voltage. And we have seen there will be some reactance to take care of JXM. Now you tell me how this component should be taken into account. Should it be represented by a series resistance connected here, or in parallel? That first you decide. In parallel. Because of what? Because this ICL component will not change with degree of loading. It is always constant. Whatever core losses is taking place, it is constant in a transformer. Are you getting? Therefore, this must be represented by a resistance connected in parallel, RCL. And then of course, rest of the things is your ideal transformer. Those thing is there. And here is your load. That is whether the secondary is loaded or not. This ICL will, this RCL will have a constant power dissipated in it. Because of what? Because we have just seen the core losses independent of the degree of loading on the transformer. So it should be represented by this, and your things will be there. Okay, so what will be the phasor diagram now? Phasor diagram will be, this is your supply voltage V1. Your this current, total current drawn from the supply during no load test is I naught. This I naught will have two components, magnetizing component, that is this is I naught, this is I naught, and this one is Im, magnetizing current, and this one is, I will call it ICL, core loss component. CL stands for core loss component of current. It is real power drawn from the supply, that is ICL into V1, and this is your no load power factor angle theta naught. In the secondary, now this is the voltage induced E1, E2, etc. E2, and your secondary current, if any, because of loading, this will be some I2, and then this I2 will have a reflected component here. You add to I2 this I2 dashed. Then you invoke all the conditions of the ideal transformer after this that we have studied, and then this will be your total primary current I1, and this is your primary power factor angle theta 1, and this is your theta 2. Therefore, core loss and the magnetizing component of the current can be taken in this fashion. Now, two things remain to be taken into account. One is the winding resistance and the leakage flux that may exist in a transformer. You tell me how to take into account the winding resistance into account. Suppose you consider a transformer which is otherwise ideal. Suppose, let us assume, you listen. Suppose let us consider a transformer which is otherwise, ideal, except that winding resistances are present. Because winding is made of copper or aluminium, so it has got some length, some cross-sectional area. So rho L by A will be the winding resistance in the winding. So primary winding will have some resistance, secondary winding will have some resistance. Now this resistance, and suppose it is an ideal transformer otherwise, that is mu R is infinite, core loss is not present, leakage flux is not there, only thing winding resistance is there. So if you are asked to take that resistance into account, and this is your supply, where you will show it? In series with this line, straight, R1. Is not? Of course, this R1, you must see it is quite small by using good materials like copper. Are you getting? But there will be some resistance which should be shown in series. Once you show it like this, to understand what is happening or how to tackle this situation, you may think that this impedance or resistance is in series with the supply. Suppose let us push it to the supply side, and this remains your ideal transformer. Are you getting? It is as if you are supplying a transformer from a source which has got some internal resistance or impedance like this. So R1 should be shown in series with this line. Now that is what the resistance part is. Now first of all, what is leakage flux, that I will explain, and then I will also tell how to take that into account. Now in a transformer, leakage flux, leakage flux. When in a transformer you wound the winding, you make the winding like this, and when it carries some current I, we calculate the flux inside the core of the transformer by telling the total MMF acting in this magnetic circuit is Ni, and Ni by L I calculate H like that, and I assume all the flux is confined. Now when you make some winding, there will be some space left between the edges of the core and the winding. There will be some air gap will be introduced, is not? Therefore, the flux line, strictly speaking, will be produced inside the core like this, several lines, but there will be some fluxes also, they will close their path like this. through the air gap. It will never, of course, because that is as if a given MMF, there are two parallel circuits. One is the reluctance of the air gap and another is the reluctance of the iron. Most of the flux lines will be confined to that because the reluctance is much less compared to the air gap. But nonetheless, if you consider a closed path here, you find some current is enclosed, some flux will be driven here, depending upon this total MMF divided by the reluctance of the air gap, etc. Therefore, there will be some leakage flux also present. Okay. This leakage flux, of course, will not able to induce any voltage in the other coil. So, leakage flux is that flux which links only the concerned coil which has produced this flux. So, this flux is called mutual flux, which links both the coil, mutual flux, mutual flux, and these fluxes are called leakage flux. Or in other words, the applied voltage, whatever you do, suppose this is the N1 number of turns, primary winding. It is d dt of total flux linking the coil. Now, while calculating the induced voltage across the coil, what flux should I take? The flux inside the core plus the leakage flux together, because both of them are linking so far as the induced voltage in the coil is concerned. So, I will now write it like this. This phi is the total flux crossing the coil. A portion of it is the mutual flux, that is the phi m. And a portion of it, I will call it leakage flux, using this small l suffix, leakage flux. Now, this can be written in this way, N1 d phi, this phi m is mutual flux, not mutual flux. So, this phi m dt will be there, and plus there will be another term N d phi l dt, the leakage flux term will be there. When I draw the phasor diagram, this E1 I have drawn corresponding to this mutual flux. This E1 always we have drawn mutual flux, because there was no leakage, of course, at that time. So, all the flux was shown like that. That is, this E2 was this one. But this leakage flux, because of that, there will be some voltage also. That is, across the two terminals of the coil, I have now this induced voltage, E1, in series with another voltage, which is N1 d phi l dt, and it is due to leakage flux. Therefore, you tell me how this leakage flux thing can be taken into account in your representation of the equivalent circuit. It can be just shown by a small inductance in series with the line, because of the fact this voltage drop due to the leakage flux has nothing to do with your energy transfer or induced voltage in the secondary. What it will do? It will only cause, that is between the two terminals of the coil, there is one small drop, leakage flux, that is N d phi l dt into N, and then there is this E1, which is your N1 d phi m dt. But this one, because it has got no magnetic coupling with other coils, can be treated as some LL into di dt. Okay. As I told you, the voltage induced in a coil is N d phi dt. One can interpret it as L di dt. That is nothing new in it. But why this I am not showing as L di dt? Because of the fact this induced voltage I am interested in to calculate. So, let us not right now bring any L concept here, because I know how to calculate induced voltage in the primary and secondary, and it is to be supplied to a load. I am interested in voltage. That I have taken care of. But so far as this thing is concerned, this can be taken into account by a leakage reactance, connected in series with the coil. Therefore, the equivalent circuit will be, so this one, you write down, this one can be thought of as a small inductive voltage drop. So this can be done as winding resistance, then some small inductance. I will describe also in the next class some leakage reactance. This is written as some XL1. Then this branch of core loss resistance, magnetizing reactance, and then comes your ideal transformer. So to conclude today's lecture, I will tell you I have discussed today one of the important things, that is the core losses in a transformer. Core losses in a transformer comprises of hysteresis and eddy current loss. Both of them depends upon the level of flux density, that is Bmax, and the supply frequency. In a transformer particularly, we know that the flux density level does not change substantially from no load to full load. Why I am using the word substantially? Because in a practical transformer, we will see that may change slightly, but not to be taken note of very seriously. We can make a general comment that core loss practically remains constant. That I will show you next class. Because of the fact supply frequency is constant, Bmax is constant. Therefore, the core loss can be taken into account by a resistive elements by connecting in series with the magnetizing branch. So today we stop here. Tomorrow